Welcome to the second lecture on alternating projection onto convex sets. As you know, we have dropped the A in the alternating, and so we only have POCS, and the POCS stands for projection onto convex sets. In the first lecture, we looked at the definition of convex sets, and we attempted to substantiate convexity geometrically in lower dimensions and then generalize it to higher dimensions, and found out that there were a lot of interesting signals that were convex, including the set of signals with identical middles, the set of signals with constant area, the set of signals with an energy less than or equal to a bound, the set of bounded energies we found out was a box in higher dimensions. And after we looked at these different signals which were convex, these different signal classes which were convex, we talked about the projection onto the signal class. And we found out that in most cases this projection was very intuitive. For example, if you have a signal which isn't bounded, you want it to be bounded between specified bounds, you just clip it at the upper and lower bound. Very intuitive. If you have a signal which isn't band limited with a bandwidth B, you simply run the signal through a low pass filter with a bandwidth B, and the output is the projection onto the convex set. If you have a signal with a constant area over an interval T, then in order to project onto a convex set of constant area, you simply raise or lower the signal so that it has an area of A. And we found out this was also applicable to the idea of tomographic projections, where the projection was equal to a line integral, or in discrete cases the sum of pixels along a specific trajectory. Now we're going to look at some of the implications of convex sets and what we can do with convex sets, and how we get into the alternating projection onto convex sets. So we'll start out with this first slide talking about the intersection of convex sets. I think you can see geometrically here that if we have two convex sets, here we have a convex set C1 and a convex set C2. C1 is kind of a rectangle, C2 is looks like a circle. And the intersection of the two is also a convex set, and that in general is true. The intersection of two convex sets is itself convex. If we look at the right-hand signal on the next slide, we have kind of a spheroid here, and we have a line segment. We decided that a line segment was an example, or a plane is an example of a convex set, because if you take any 2 points on a line, or any 2 points within a plane, and you connect those 2 points, then that line segment is totally subsumed in the convex set. So here we have kind of a spheroid, we have a line segment, C2, and the combination of the two, the intersection of the two, is the little line segment C1 intersected with C2, which itself is a convex set. So the intersection of convex sets is itself convex. We talked about the projection onto convex sets, and here we have the interesting general result of POCS. If we take two convex sets and we alternately project between the two convex sets, we talked about projection last time, then we will end up as a fixed point in the limit at a point which is in the intersection of the convex set. That is really cool. So if you look here, we start in the we start at the top, we project onto C2, then we project onto C1, C2, C1, C2, and you can see that eventually we're going to work our way down to the star. There's an orange star there which you can see, and that orange star is where this projection is going to converge. And that is the cool part of POCS. Alternating projection between convex sets will always converge into a point in the intersection of both. Now, if we start at a different point, say for example in this figure that we started at the point, the purple point in the lower part, and we then projected onto the convex set C2, it looks like the next convex set projection onto C1 almost gets us to the fixed point, which in this case is shown by the purple star. So We are not guaranteed to always converge to the same point. It depends on the initialization. But we are assured to converge to a point which is common to the intersection of the two convex sets. This generalizes to 3 or more convex sets with non-empty intersection. If you alternately project between the convex sets, you will end up at a point that is in the intersection of all of the convex sets. Now, let's see if we can do this. Remember the set of bounded signals, and we just had 3 points in the signal set, so we could deal with 3-dimensional sets. We decided that the set of bounded signals was a convex set, and it turned out to be a box. And then we had the constant area signals, where if we added up the signals, we got a constant. In this case, we're going to add up the 3 values, and it's going to give us a value of 2. And those are 2 convex sets. Now, at the top here, we have a starting point. And this starting point has, it looks like 6, 6, and minus 1 as the starting point. And so the first thing we're going to do is we're going to project onto the set of bounded signals. Now, the set of bounded signals, if you recall, if we bound them between 0 and 4, corresponds to simply clipping the signals at the upper and lower bounds. So we clip the signals here at the upper bound of 4 and the lower bound of 0. That's kind of cool. Now we need to project onto the constant area. Remember, the constant area projection is taking the signal and adding or subtracting from it so that it has the desired area. In this case, the desired area is 2. So that's what we're going to do. We are going to actually lower the signal, as you can see in this projection. We're going to lower the signal so that the upper value is now equal to 2 and the lower value is equal to minus 2. So notice we've simply taken that 404 and we have lowered it a value of 2. These 3 points add up to 2. 2 minus 2 plus 2 is equal to 2. So it works. We do have a signal which sums to 2. Now we need to project onto the set of signals which are clipped. And that's what we're going to do. We're going to bound the signal. Now one of the elements of the signal that we just projected onto is below 0. And we're going to take that signal and we're going to clip it to 0. That's what we do in our next projection. Now we have to take this signal and we have to raise or lower the water level in order to get it a value of 2. You notice that currently it sums up to 4, which is much too big, so we need to lower the water, if you will. And in order to do that, it turns out that we get a value of 1 1/3 for the upper 2 points and minus 2/3 for the bottom points. And notice 2 times 1 1/3 minus 2/3 does equal to 2. It's a little awkward, but indeed this is within the set of signals whose sum to 2. Now what do? We clip it again, and notice that bottom one now is below 0, so we have to clip that off and only keep the top. And so you can see what we're doing. We're alternating back and forth between these 2 convex sets, and we are assured that there is an intersection. All you have to do is give an example of an intersection. Now if we were to carry this iteration on, very simple iteration, clipping, raising or lowering the water level, clipping, raising or lowering the water level, we would converge to the value which is shown here on the bottom, which the first and the second term would be equal to 1 and the middle term would be equal to 0. That is indeed the result we want. And it certainly is within the 2 convex sets. It's within the bounded set, and it's within the set that adds up to 2. Very good. So lemma 1, alternating POCS, projection onto convex sets among n convex sets with a non-empty intersection, will converge to a point common to all. We can see that on the following slide. We have 3 convex sets. We have C1, which is an ellipse, C2, which is a line segment, and C3, which is, 2 home plates joined together. And you can see if we project onto C1, then C2, then C3, and we keep on going, we end up at this pink star. Now what is interesting about these 3 convex sets is that they only have 1 point of intersection. there's only one point that is common to all three convex sets. So if we're assured to always end up at a point common to all three convex sets, then no matter where we start, we're going to end up at that pink star fixed point, which is shown here. No matter where we start, we're going to end up at the fixed point. So you can see here that we started at a different value at the pink circle in the lower right-hand corner, and we projected onto C1, then C2, and you can see that we got home to that fixed point, that final limit point, very quickly. And it doesn't matter where I start on this plane if I alternately project between these three sets that only have a single point of intersection, that I am going to converge to that single point which is common to all of them. There's a very interesting special case of this called von Neumann's alternating projection algorithm, put forth by the genius von Neumann. Von Neumann had a lot of great contributions, including to the von Neumann architecture for computers. He was one of the first to recognize Gödel's great proof in the 1930s, which derailed a major effort in mathematics at the time. But here was von Neumann's alternating projection algorithm. Suppose that we have two or more planes that intersect. Now, if you have a bunch of planes which intersect, they are going to intersect another plane or a line. It does turn out that if you have a point external to that intersection, which is here shown by the vector y, that there is clearly going to be a point which is closest to the value of y within the intersection. In this case, it's given by the black star. There is a unique point in the intersection that is closest to the vector y. So, von Neumann's alternating projection algorithm says that if you apply POCS, starting at that point, that the alternating projections will converge to that point. And we see this in the following figure. We have converged to the point corresponding to the black star by projecting onto C1 or C2, then onto C1, C2, C1, etc. Now, up to now, we have assumed that all of the convex sets have intersected. Well, what if they don't? Well, let's start with the simple case where there are two convex sets. So here we have C1 and C2, and there's no intersection between the two. The two convex sets do not intersect. It does turn out that alternating projection among two non-intersecting convex sets will converge to the point in each set closest to the other. In other words, we generate the limit cycle, which is shown here. You can see we start with this orange spot in the upper left. We project onto C1, then C2, then C1, and then we bounce back and forth between C1 and C2. It turns out that the point in C1 that is closest to C2 is that final fixed point, and vice versa. The point in C2, which is closest to the set C1, is the point in this limit cycle. And we bounce back and forth between these limit cycles. So we have found the best solutions, at least in that sense. But what good can we make of it? Well, before we talk about that, let's extend this now to three convex sets and what happens when you have three non-intersecting convex sets, as is shown in this slide. We have C1, C2, and C3. Now, if we project onto C1, C2, and C3, we will also end up with a limit cycle, this time a triangular limit cycle, which is shown here in white. So we go from C1, and then C2 is the closest point in the triangle, and then we go to C3 and C1 again, and we have reached a so-called limit cycle in terms of the projection. The sad part about three or more convex sets is that the limit cycle is not unique. Suppose, for example, that I reversed the order of projections, and I did not project onto 1, 2, 3, but I projected onto 3, 2, 1. Well, it turns out if I project onto 3, 2, 1, I get a totally different limit cycle. And what does that mean? Look at it. Is there something in common to those two limit cycles? There possibly is, but I don't know what it is. There's other ways to deal with this sort of thing. So alternating POCS among three or more convex sets with an empty intersection will converge to a limit cycle, and different projection operations can produce different limit cycles if you do them in different orders. Even if two of the sets intersect and a third one doesn't, you can get limit cycles, and that limit cycle can be different if you change the projection of the convex sets, as is seen in this slide. So how do we deal with this? This is a very common engineering occurrence. You come up with a design, and you know that this design cannot meet all of the constraints that are required in the design. So if that's the case, one knows that one must compromise among the different constraints. And we can do this with a process called simultaneously weighted projections, which is illustrated in this slide. For simultaneous weighted projections, we don't take alternating projections. Rather, as shown, we take a value, a signal value, and we project onto C1, C2, and C3. Now these are going to be vectors in the space, and we can actually compute these vectors connecting Y with these convex sets, and we can average the three projections. And that's what we're going to do in the next slide. We're going to take the average of these three projections. Well, that's nice, but what good does that do? Well, it turns out that we can now repeat that process. We can take the new average and we can generate the projection to the three convex sets, and then we can take the average of those three projections. If we repeat that using simultaneous weighted projections, it turns out that we generate the minimum mean square error solution or compromise to the convex set constraints. So simultaneous projections allow us to get a minimum mean square error solution to constraints which we can't meet simultaneously in the case where the convex sets don't intersect. In fact, we can actually have one of the constraints be more important than another constraint, as you see here in this next slide. Rather than just average them, we can perform a weighted average. And the weight on the average becomes larger depending on how important that constraint is. Maybe one constraint is three times as important as the other constraint. So we can actually choose those different values of weights in this simultaneous weighted projection. Then you get the minimum mean square error solution using those corresponding weights. So we can use a weighted average. If we do use a weighted average, you can see the formula in the purple box. If we do use the average, that means that each of the weights on the projections is 1 over n, and it does give, in all cases, in the limit, a minimum mean square error solution. So we do have a nice way of dealing with POCS in the case where we don't have the ability to satisfy all of the constraints dictated by the convex sets. So I think that will wrap up this lecture. What we have done is we have overviewed the basic math of alternating projection onto convex sets. We have looked at, in the first lecture we've looked at convex sets and defined some of the convex sets, and now we've looked at intersections of those convex sets. What alternating projections can do. We found that alternating projection between a number of intersecting convex sets will always converge into a solution that satisfies all of the convex constraints. On the other hand, if the convex sets don't intersect, we are left with the problem of finding a compromise, and the process of simultaneous weighted projections allow us to look into this compromise, specifically obtaining a minimum mean square error solution to the convex constraints. Next time we'll look at some actual applications of POCS, and I think this is maybe the most fascinating aspect of the lectures. So we'll talk to you then.